So I'm Matt Begat-Conway. I'm an assistant professor of city and regional planning at the University of North Carolina at Chapel Hill. I worked on this project with Manuel Santana Palacios, who's also here on the call today. He's now an assistant professor of planning at Ohio State University and was a postdoc here until recently. So today we're talking about the transport implications of online shopping and delivery services. And just to kind of give some context and background, most of us are probably familiar with this, but just to kind of put some numbers on what we already know, e-commerce has been growing over the last 10 years. And these are just some numbers from the US Census Bureau that show kind of a steady rise in e-commerce over the last decade. Of course, a big jump at the start of the pandemic, some tapering off as some of the pandemic restrictions were eased, but then this trend is expected to continue upwards. So regardless of what the transportation implications are, e-commerce seems like it's here to stay. And what the transport implications are, online shopping, depend on at least three factors. So how far those delivery vehicles are actually traveling on the network, because that's creating traffic on the network, wear and tear on the roadway, and so on. And there's a lot of good research already out there about that, using simulation models for looking at different configurations of depots, speed of delivery, next day, 2-day, 3-day, how much flexibility there is in delivery, things like that. But the other two factors are how far people are traveling to shop in person, because if we don't know that, it's very difficult to compare e-shopping with in-person shopping. And then the marginal rate of substitution between e-shopping and in-person shopping. So it could be that an in-person shopping trip is just replaced one-to-one with an e-shopping trip. But you could also imagine that in some cases, a single in-person shopping trip might be replaced by multiple e-shopping trips, for example, because it's much easier to just order something on Amazon from your phone than it is to go to a store and buy something. So whereas you might go to a store once every week or every 2 weeks for buying some kind of durable goods, you might make several Amazon orders a week because it's just so easy to do that. Alternately, you might have cases where you need 5 things and you would have had to make trips to 5 different stores to get those in person. But because of the scope of e-commerce sites online, you're able to make a single e-shopping trip to replace all 5 of those in-person trips you would have had to make for those hard to find items. And so in this study, we really looked at these last 2 items. So how far people are traveling to shop in person, and then what that marginal rate of substitution might look like. So these were kind of 2 separate arms of this project using different data sets. So I'm going to talk about them sequentially. And first, I'll talk about how far people are traveling to shop in person. And now the reason why this is difficult to figure out and why there's not a clear answer in the literature is that most shopping is occurring in trip chains. So shopping trips are chained either with other shopping trips. People are making a shopping tour where they stop at several stores, or making things more difficult to estimate, being chained with other non-shopping trips, for instance, stopping at the store on the way home from work. And in those cases, it's very difficult to determine how much distance was actually traveled for shopping versus other purposes. There's several existing techniques, which I'll go over here in a minute, each of which has its own problems. Probably one of the most common methods is the shopping destination method. This is really common with reports coming out of travel surveys. And what this does is for each trip, you look at the trip destination purpose. And for all the trips where the destination purpose is shopping, you just sum up the total distance of all those trips. If you did just make a simple round trip to the store and not chain your trips, that's going to underestimate that travel distance because it's not going to count that return trip, because the trip to the store had a purpose of shopping, the trip home had a purpose of return home. But you wouldn't have made that second leg of the trip if you hadn't made that first leg to go shopping in the first place. So in a situation like that, it's going to underestimate the distance. In trip chains, it's more complicated. It might over or underestimate the distance. It could, for instance, overestimate the distance if you drove, for example, 19 kilometers from work to a store and then 2 more kilometers home. It's probably not accurate to say that you drove 19 kilometers to go shopping, because most of that distance was moving you towards home, and then you just stopped near your house at a store. And that's going to attribute more distance to that shopping trip than really should be, because it may have not added any distance at all to your work trip that you were making anyways. Another method that gets used is the round trip distance method, which is just looking at the locations of the stores and assuming that each shopping activity requires a round trip from home to the store. Of course, if trips are chained, whether with other shopping trips or with non-shopping trips, that's going to overestimate the distances because, when you have multiple stops on a tour, that's going to be less than the round trip distance to each of those locations. Some authors account for this by multiplying by a correction factor, so between a value between 0 and 1 that reduces that round trip mileage based on how much trip chaining is expected to occur and is expected to reduce total travel. But of course, figuring out what that correction factor should be is pretty difficult. So what we did is we used what we're calling a marginal distance method, which is where we created counterfactual tours. We used travel survey data where we had detailed latitude and longitude information for all the stops. And then we used a routing engine to estimate the travel distances for what people actually did, but also what people would have done, in counterfactual worlds where they only went shopping or didn't go shopping. So for a tour that mixed shopping and non-shopping activities, if the tours were primarily shopping and had some incidental stops, for instance, you went shopping, but you also stopped for lunch, we would reroute that trip with those incidental stops removed. So in this case, you stopped for lunch and you went to the post office, which we're considering an errand rather than shopping. And so in this case, the original trip here is shown in blue. This is what you would have done to go to all of these locations. But if you remove the restaurant and the post office, you would have taken the trip shown in yellow here, which is significantly shorter. And we would attribute only the distance of that trip shown in yellow, or excuse me, that tour shown in yellow to the shopping purpose. For tours that were mixed shopping and non-shopping, where the primary purpose wasn't shopping, for instance, a work tour, we would reroute the trip with the shopping stops removed. So in this case, someone went to work and then to a hardware store and a department store and home. And I should note, these are all hypothetical trips. This isn't actual survey data, so there's no privacy concerns here. We removed that hardware store and department store from that tour and routed just the round trip to work, that's shown in yellow. And then we took the difference of those. So we said the actual distance traveled minus the distance that you would have traveled if you hadn't gone shopping is the additional distance that was traveled to go shopping on top of what you would have been doing anyways. We used data from the 2016 Triangle Travel Survey, which was done in the Research Triangle region here in North Carolina, so Raleigh, Durham, Chapel Hill area. And this was 1 weekday of travel. Unfortunately, the survey didn't capture weekends, which would be really useful for shopping travel, as a lot of shopping does occur on the weekends. And we had about 4,000 households in this survey. And looking just at the results, we see that both the mean and the 75th percentile of overall household daily shopping travel, and this is vehicle kilometers rather than person kilometers, it's about 11 kilometers a day in this region. And the reason we were reporting the 75th percentile here is because the mean is pretty sensitive to outliers. So there's some very long shopping trips that are, probably shopping trips that are occurring as part of a longer tour of some sort, but that isn't necessarily reflected in our data, where, you drive a long distance to go someplace else. And so the 75th percentile is not sensitive to those outliers. The median is 0 because most households don't shop on any given day. And we can see that that's significantly less than the round trip distance and fairly similar to the shopping destination method. So all of that is not really part of the current project. That's a previous STRIDE project, but it's important background to understand what we did in this project. And so the first part of what we did in this project was to decompose the shopping travel. So this number is just 11 kilometers a day, doesn't really tell us a whole lot about what's contributing to that, particularly since this is at the household level, vehicle kilometers. We don't know, what types of shopping trips those households were making, what their demographics were, and so on, based on just this number. So we know that shopping travel is heterogeneous. Different people who live in different places, who are making different kinds of shopping trips, are going to travel different distances for shopping. So to kind of decompose this household level daily shopping travel, we regressed it onto the types of trips folks were making, characteristics of the household, and the built environment where they live. We used ordinary linear regression as well as quantile regression for the same reason that we were using the 75th percentile before. It's not as sensitive to outliers. And we excluded from this analysis any households that didn't shop on the travel day. So we're only looking at the distance traveled for households that actually did travel for shopping. So just to very briefly talk about what quantile regression is, if anybody isn't familiar with that. So the coefficients in a standard linear regression are predicting the mean. So if you take, a person with a set of characteristics and you use the linear regression to make a prediction of them, of their behavior, that should be the mean of, all people who have the same characteristics. In a quantile regression, it's very similar, but instead of the predicted value being the mean, it's a chosen quantile. So very often that's the median, but also a lot of times folks will run multiple quantile regressions for different quantiles because it allows you to see how effects are different for households at the high and low end of the travel distribution. And that's what we did. We ran quantile regression for the 5th, 25th, median, 50th, 70th, 75th, 95th percentiles, so that we could look at those differential effects. And then quantile regression, of course, is less sensitive to outliers than the standard linear regression is, for the same reason that the median is less sensitive to outliers than the mean. So dig a little deeper into our specification of our regression. Our dependent variable was the total household shopping vehicle kilometers of travel on the travel day. So how far they drove their vehicle or vehicles for shopping. Our independent variables were trip counts in different categories, different types of shopping, sociodemographics, and then built environment characteristics from the EPA Smart Location database. We estimated all of our regressions without an intercept, and so that those trip count variables are interpretable as the travel distance for that type of trip. So there's no intercept that's contributing to the travel distances. So you can just read off from our particular trip type what the length of a trip like that is. And we entered all of our trip type variables as the counts of trips in that category. So those coefficients are all per trip rather than overall for a household that made any number of trips. And then we interacted all of the sociodemographic and built environment variables with the total shopping trip count. So all of the effects of sociodemographics and built environments can be interpreted per trip as well. So any coefficient that, is a coefficient of +1 would be associated with, means that's associated with a 1 kilometer longer travel distance for each trip. So in our base model, where we just had the trip count variables and don't have any of our other covariate, we see results that look something like this, which isn't that surprising. You have things like pharmacy, grocery, gas, and convenience stores having shorter travel distances than trips to purchase durable goods or go to warehouse stores. This other category here is trips that we weren't able to categorize. The Triangle Travel Survey didn't have this detailed of a categorization of shopping. So we used the names of each of the shopping locations to categorize these. And those are the ones that we weren't able to easily categorize. And then these errands here are things that where folks reported them as shopping, but when we actually went and looked at the destination, they went to a doctor's office or something like that, which are probably miscategorized. And ultimately, we'd like to go back to the original shopping data set and recalculate that with distances with these correctly classified as errands rather than shopping. And that's something we're planning to do in the future. So the main takeaway here is, not surprisingly, there's heterogeneity between different types of shopping, with things like durable goods and warehouse stores having longer travel distances than more frequent shopping trips. And this is for the regression at the median. When we look at the 95th percentile, so these are the effects for folks who are traveling a really long shopping distance overall, we see that they're, fairly similar results. The pharmacy, grocery, convenience stores contribute the least amount of travel, even for people who had very, very large amounts of shopping travel. The one that's a little confusing here is gas, which has a coefficient around 60 kilometers. Because gas is fungible, it doesn't kind of pass the smell test that you would travel that far for gas. And we think that this is actually a bit of an endogeneity problem at this high percentile, which is that when you're making a really long trip, the longer your trip is, the more likely you are to have to stop to buy fuel in order to make that trip. So we think that the model is picking up on that here. And then the 5th percentile results are interesting because these are folks who are going shopping, but traveling very, very little to do so. And a lot of these are probably trips that are really happening on the way to someplace else. So like this, the coefficient here for gas is very close to 0. And that's probably because people are, just pulling off the road, whatever road they're driving on, into a gas station rather than adding much travel to their trip. But other things like warehouse stores, for instance, even at this low percentile, add a fairly significant amount of travel or are associated with a significant amount of travel. When we added sociodemographics to this model, and the 4 we included were home ownership, the number of adults in the household, the number of children in the household, and income, we found a few relationships. The number of children, consistently negative relationship with shopping trip travel length across our regressions. And that's statistically significant only at the median 75th percentile and mean. So I think it's a little bit questionable how much we can read into that. Similarly, income is consistently positive across all regressions, but only significant at the 25th percentile and in the mean regression. So overall, most of the sociodemographic variables were insignificant in most of the regressions we ran, which leads us to believe that differences in travel are probably more related to the type and number of trips people are making, because that's controlled for in the models, the number of grocery trips, the number of warehouse trips, rather than the length of the individual trip. So that suggests that a lot of that heterogeneity we observe in overall shopping travel across the population is not driven by people traveling further on individual trips, but because people are making different types of trips and different amounts of shopping trips for folks in different sociodemographic categories. Most of the built environment variables were not statistically significant. The one that was the regional accessibility index, which ranges from 0 to 1. This is a measure of job accessibility by car. And it's just the job accessibility by car divided by the maximum in the region. So 1 is in the most accessible location in the region, and then it falls off from there. This has a statistically significant and large negative association with shopping travel, but only at the higher percentiles. At the lower percentiles, even at the median, this is not statistically significant. The effect is highly significant and very large when you're looking at for instance, the 95th percentile. And so what we interpret that as is that the people who live in central areas are traveling about the same as other folks for their shorter trips, their daily trips, the grocery store, whatever. But their longest shopping trips are shorter than the longest shopping trips of other folks. And we think that's fairly consistent with geographic theory. So central place theory is basically the idea that there's this hierarchy of places, and higher order places have more opportunities of all types, but are going to have more specialized stores, for example. So folks who are living in a central area are likely to be close not only to a grocery store, which grocery stores are fairly ubiquitous, at least across the triangle, but if you're living in a very central location, you're likely to be close to some more esoteric stores, that stores for durable goods, specialized durable goods, warehouse stores, and so on. In terms of what does all this mean for policy? So because of these differences between the amount of travel that's associated with different types of shopping, that means that the travel implications of e-commerce are going to depend a lot on what kind of shopping actually happens online. So if online shopping is replacing trips for durable goods, which I think is a very large part of online shopping right now, or even warehouse stores, that's going to have different travel implications than if it's replacing trips to 7-Eleven or the gas station. You can actually buy gas online. There is a company that will sell you gas online and come to your house and put it in your car. And because of how much heterogeneity there is in travel across different types of shopping trips, travel demand models need to have more granular trip types to model shopping. So frequently now, travel demand models will just have a single, home-based shopping trip type, something like that. But if we want to really do scenarios around e-shopping, we're going to need to make it more granular than that. If you're just interested in kind of predicting current conditions or predicting future conditions under the status quo, that might not be as important because that average is going to be, representative of that distribution. But if you are starting to talk about shifting trips between shopping modalities, then it's going to become important to be able to model those different distances traveled for different trip types. And before I move on to the next section where I'm talking about marginal rates of substitution, I just wanted to pause for a moment and see if there were any clarifying questions about this section before we move on. Feel free to put those in the chat or the Q&A, and I'll give a minute for folks to type those in if they are interested in doing so. Right, I'm not seeing any. Feel free, if you're still typing, just keep typing and I'll come back if I see something pop up over there. So now I'm going to talk about the second portion of our study, which is looking at the marginal rates of substitution for e-shopping and in-person shopping. So online and in-person shopping substitution patterns are, as I mentioned before, not necessarily a simple one-to-one relationship. Increased online shopping may not directly substitute for in-person shopping. It might substitute for, more than one or less than one trips. In some ways, online shopping could even complement in-person shopping. Maybe you look for something online and find that it's available at a store nearby where you can go get it today and you don't have time to wait for delivery. Or you go to the store and they don't have what you want, but they say you can order it from them online, things like that. So in some ways, they could actually be complementary, and increases in one might be associated with increases in shopping overall. And I mentioned how the substitution might not be a one-to-one substitution. Now, the really big challenge with figuring this out is differentiating within and between person effects. So in a cross-sectional study, so a study that uses a survey, for instance, that's done at a single point in time, so you have one observation, one survey from each respondent, you often find that in-person and online shopping are positively correlated, which could indicate they're complementary, that increasing online shopping makes you increase your shopping overall. But it could also be just because heavy buyers, people who shop a lot online and in person. Regardless of modality, heavy shoppers are going to shop a lot online and in person, for example. So we need to distinguish between that between-persons effect, which is that people who shop a lot by any modality, from a within-persons effect, which is that because I shop online, I then don't need to shop in the store as much, holding my overall level of shopping activity constant. So this is very difficult to answer with a cross-sectional survey. So we used the COVID data from the COVID Future Panel Survey, which was a longitudinal survey that was conducted in 3 waves. The first one in summer of 2020, and the second one in winter of 2020 through 2021, and the third wave in fall of 2021 into spring of 2022. And this survey asked respondents a whole bunch of things, but relevant to us, asked about their pandemic-era travel behavior, and specifically questions about online and in-person grocery shopping and restaurant dining. And then we're using what's called a cross-lagged panel model to model this. And so this is a structural equation model, and that just means a model where you have more than one dependent variable, basically. You have 2 variables that are observed at multiple points in time. In this case, we have the online and the in-person behavior observed at each of the 3 time periods. And then you structure your model so that each variable influences itself and the other variable at the next time period. So graphically, that looks something like this. You have in wave 1, you have your observations of in-store and online shopping. In wave 2, you're expressing in-store shopping as a function of in-store shopping in wave 1. So that's kind of like a measure of habit or some kind of baseline. And that's called the autoregressive coefficient because you're regressing in-store shopping on itself in a previous time period. And then you have these, which are the more interesting coefficients. These are the cross lags. So this is telling you how much an increase in online shopping in a particular wave is associated with an increase or decrease in in-store shopping in the following wave, and of course, vice versa for this coefficient. So if this is positive, that would indicate a complementary effect, that increases in online shopping are then associated with increases in in-store shopping in the next wave. If this is negative, it would indicate a substitution effect. So that's how the cross-lagged panel model works. It's gotten more traction in transportation recently. It's been around in other fields for a long time, but this is, I think, a really good method for looking at panel data like this and understanding this complementarity and substitution. So looking at groceries, the survey asked the question about in the last 7 days, how many times did you personally shop for groceries in a store and shop for groceries for delivery? And the frequencies were all converted to binary variables for this. So these were asked in a couple of categories, 0, 1, 2 or 3, and 4 or more. We just converted that to a simple 0, 1, you either did or you didn't. We did do a sensitivity test where we specified these as continuous and categorical variables. They didn't change the interpretation, so we just stuck with the binary variables because those are kind of the simplest to interpret. And these are our model results. And you can see that the autoregressive coefficients, as we would expect, are positive and statistically significant. People who, that indicates kind of like the baseline behavior is somewhat consistent. And what's interesting here are these cross lags. So all of the cross lags are negative and statistically significant for groceries, which indicates evidence of a substitution effect for groceries. So increases in in-store shopping in one time period are associated with decreases in online shopping in the next time period. And because of the autoregressive coefficients, we can interpret that as a within persons effect, because we're effectively controlling for the between persons effects with those autoregressive coefficients. We're controlling for what they did before. So that's pretty interesting. That shows that for groceries, you're seeing a pattern of substitution. The effect sizes are fairly small. These coefficients are unstandardized. So what this means is that, for instance, a 10 percentage point increase in in-store shopping is associated with a 0.9 percentage point decrease in online shopping. So that's not a huge effect size and not super economically significant, but I'll talk a little more about why that might be in a minute. But the effects are all negative and statistically significant, which suggests that there is at least some degree of substitution going on. The restaurant model, the data was very similar. It's in the last 7 days. How many times did you personally eat a meal in a restaurant and order food for delivery from a restaurant? And we again converted those frequencies to binary, and the model didn't really change if you specified it with those frequencies in another format. And that model looks like this. So as before, as expected, the autoregressive coefficients are statistically significant and positive. The cross lags are mostly insignificant. The one here that is marginally significant at the 10% level, but only very marginally significant. So there's not really strong evidence here for either complementarity or substitution between dining in person and getting takeout. And the effect sizes, again, are very small and even smaller than we observed for the groceries. The major limitation of all of this is the survey itself. The survey waves were spaced several months apart, which when you're talking about substitution or complementarity, means all our model can capture is trends towards increased online shopping, an overall over time increase in online shopping being related with an overall over time decrease in in-person shopping. It can't capture actual direct substitution effects. For instance, if you buy groceries today, that might mean you don't need to buy groceries online tomorrow, but buying groceries today in the store is not going to be a direct substitute for groceries you might buy online in 2 or 3 months when the next survey wave comes along. So that's one area of future research, would be to use a data set that had a bit more frequency for this. We also have a lack of information on durable goods purchases, and durable goods are probably the most popular thing to buy online. They're the simplest thing to ship. They're not perishable. And so that would be a major, contribution. There's also likely to be, it's not that surprising that groceries have a substitutionary effect, because there's kind of a somewhat fixed amount of groceries that a household needs based on the household size, whether the household includes teenagers and so on. Whereas there's presumably a lot more variation in how much durable goods are being purchased by different folks. And of course, the COVID Future Survey was also done during and in the early kind of aftermath of the pandemic, which potentially distorts some of these patterns, particularly since online shopping became such a big part of many people's lives very quickly, right at the start of this survey. So for future research on this topic, the cross-lag panel model, I think, is a really promising approach for looking at this, but we really need to look at this with better data. The clear, better data set that we could use is credit card transaction data, and I'm hoping to do some work with that data set. It's a little hard to get that data, and it's expensive, but it contains a lot of detail about what we're looking at. It's going to contain all of the purchases that people make for durable goods, groceries, restaurants, assuming they use their credit cards, which at least for online purchases is fairly ubiquitous. For in-person purchases, less so. And it's at a very high frequency. We could look at, substitution patterns within a single week, for example. So that's a big area of future research. Because of those limitations, the implications are, I think, more about the implications for research than the implications for policy at this point. But I think it's kind of clear that modeling e-commerce requires us to understand this substitution and complementarity, and it's not clear that they're simple one-to-one substitutes or complements, but more research is needed, and I think this method can really lay the groundwork for doing additional research in this field with a more appropriate data set. That's the end of the presentation here. I wanted to thank Deborah Salin at Arizona State, Carol Vulgaris at Harvard, and Zuri B. Garcia here at UNC for assisting with earlier portions of this project. The entire COVID Future Survey team, which included myself and Deborah and many others, and that was funded by the Alphabet Soup down here. And then Lita Hunsinger at NC State, who provided the Triangle Travel Survey data, funded by this other set of Alphabet Soup here. And with that, I'll open it up for any questions, comments, concerns, philosophical thoughts on the meaning of life. Feel free to use the chat or the Q&A, and I'll make sure I repeat the questions so everybody can hear them. So we've got in the context, I've got a question here about the context in the first model about whether we're talking about long-term and short-term substitution, what we're really capturing here. I think what we're capturing here is trends. So we're capturing a long-term substitution of not individual items, but we're capturing long-term substitution patterns of online and in-person shopping. So if you're, over time trending towards doing more of your grocery shopping online versus in store or vice versa, we're going to capture that in our model, but we're not going to capture that specific substitution of a specific good. We're capturing substitution more at the level of the lifestyle. And do I think credit card data would reflect what we found in the model? I think that it would reflect on the grocery side. I think it would reflect what we saw in the model. I think the effect sizes would probably be larger because I think the substitution is probably fairly strong for groceries because there's only a limited amount of groceries that a particular household needs. For the restaurants and for durable goods, I'm really not sure what we would find with credit card data. I think that the increased frequency of that data would potentially find different results, but I'm not sure what those results would be. And the next question here is about the prices online and whether online prices, which are often a better deal, were considered as part of the model. And we didn't have information on that, unfortunately, but that is a really interesting point because if we were using credit card data, we would have at least some information on the prices. We wouldn't necessarily know exactly what they purchased, but we would know how much they spent. So that's a really, really interesting point. Thanks. So thanks everyone for attending. And with that, I guess I'll let you get back 20 minutes of your Thursday and have a great rest of your week and weekend. Thanks for stopping by.